Good morning, everyone. Welcome to today's episode. This is a follow-up to the previous episode that we had on Professor Ewe and Emmanuel's birthday. Still talking about the definition of a gravitational wave. Today we want to look about a very popular concept that cuts across classical mechanics, the whole of classical electrodynamics, through also quantum mechanics, and here now we're having it in general theory of relativity. Now, the Lagrangian formulation of the theory of gravitation is what we'll be looking at. Generally, from classical mechanics, we define the action to be this, and the minimum of this action is referred to as either, the minimum of this this integral actually, or the action, is what we refer to as this S of S comma T, or the dynamic phase. Of course, when this is being extremized, we will obtain the equation of motion, popularly known as the Lagrange equation. We made the cycle Lagrange transformation to transform this to this. Of course, the popular formula in classical mechanics, and then we'll be able to write this in this form. The variation also eventually will lead us to these two equations. Of course, that's what we have in the next step. So we have two variables by which we are extremizing this integral, the p and also the x. We are going to equate each of these coefficients to 0. We will require this to vanish at the endpoints, as we always do. Now, essentially, very quickly, as we are moving on, we can apply, and it has actually been applied in general theory of relativity by Hilbert himself, the Hilbert variational principle, and I will be doing this in terms of the Christoffel symbol, or what we call the connection tensor, and then the metric tensor too. So now, of course, we know that the integral we have to solve be using this. The integral we are going to be using is this. This is what we call the Hilbert Lagrangian, or written in a better form, this is what it is like. So generally, I'll be using the notation found in the very wonderful textbook of Charles Misner-Krypton and John Archibald Miller. Now, this Lagrangian also is what we are going to be varying. This is the Riemann tensor, or we can call it the Ricci scalar or Ricci tensor. But the full Riemann tensor is given by this. Of course, we can perform a contraction, which we shall do shortly, to be able to have it in this form. And now, generally, what we have in tensor analysis, when you have this G without the indices labeled on them, on G, we refer to this as the determinant of the metric tensor. And having to use this to multiply this gives us a density. And of course, we shall see how very important this density is in the definition, or using it to manipulate tensors in general. So we are going to vary this, this integral. Just like we vary Broder integral in classical mechanics, we shall see in a moment also how we do that in classical electrodynamics. Now again, but then just like we did here with respect to p and x, we are doing it with respect to the Christoffel symbol and the metric tensor. The Christoffel symbol is contained, of course, in the Ricci tensor. Now we have some of the variations here being illustrated. Of course, we've shown how we define a Lagrangian in this form. The Lagrangian density actually, due to the presence of that minus g, square root of minus g. The contraction of the Riemann tensor to give us this Ricci scalar, or the Ricci tensor. And then also we have this variation. The variation of the metric tensor, the determinant of the metric tensor will give us something like this. This is what you obtain when you perform this very simple variation, just a little step. Now, if we perform the variation also of the Riemann tensor, this is what we obtain. Or if you decide, you can perform, of course, which we shall need also, because that's what we have in our integral over there. Performing this for the Ricci tensor, this is what you obtain. And incidentally, the Christoffel symbol or connection tensor is not a tensor. However, the variation is a tensor. So with this variation, knowing that you're going to be needing this, if we perform this variation of this integral, this is just a little step. The first step we shall have is one for this particular one, having to do with this Ricci tensor. And then we have the other one also for the field. Now, having to do this is just like, of course, what follows here is a great deal of, not very great deal actually, but there's some step that will be worked out very easily from here to here. And then what you have in the end are, again, coefficients of something here, which is the metric tensor. And also, here we have what we have to be the variation of the connection tensors. But we will have to, in a way, make some definitions that will help us in trying to solve this problem. First, we are going to redefine some of the tensors in form of tensor densities. Why is this important? We are going to give a very simple example here, given also by Misner, Thorne, and Wheeler. Now, you have this here to be a tensor that has been defined with this especially. For instance, if you were to perform the covariant derivative of this tensor, this is what you will obtain for one of its components, 0, 1, 2, 3, with rho and all that. Now, this covariant derivative, or maybe the tensor alone on its own, has this many components. Now, any of the covariant derivatives has just this many components, just a single covariant derivative. But supposing we consider the covariant derivative of the determinant of the metric tensor written in this form, that's the minus the determinant, the square root of the minus of the determinant of the metric tensor. You have that for its covariant derivative, this is what you have. And this just has 4 components. And these 4 components, as a matter of fact, takes care of the 1,024 components that you have for every covariant derivative of this tensor. So you can see the enormous amount of reduction in the amount of objects or tensors that you will have to deal with in manipulating this variation. So which is why it is very important for us to perform this, and eventually this is what we will have to do. We have to do that. Okay, also maybe if we want to define our energy stress tensor, we could define that as a density tensor by multiplying it by these objects. That's the square root of the negative of the determinant of the metric tensor. The same also if you want to define a vector density using a different symbol, of course, you note that it will simply be the multiplication of this current density, as you know before, with just this object. The same also applies for the metric tensor itself. So if you want to find the metric tensor density, you just have to multiply it with this. So it goes on and on in general for any arbitrary tensor. Now, when this is done, we will have to perform the variation of this integral, of course, as we have just succinctly illustrated here. When we perform this variation with respect to the Christoffel symbol, we obtain the very famous form or definition of the connection tensor in terms of the metric tensors. And this is what we really expect for a Riemannian geometry. And if you were to perform the variation again with respect to the metric tensor, then it yields all 10 components of the N-field equations. Now, if you remember from last time when we wrote some of the N-field equations and some of the tensors that we could find in general theory of relativity, this was one of those equations, whereby this terms here in the bracket represents our stress energy tensor. Of course, from this, everything that we've done cumulates into the Bianchi identity that we have in this form. So this in general illustrates to you what it means like to perform some of this calculation in GR. Just applying some of the principles we have right from classical mechanics up to general theory of relativity. So very quickly, let us see how this all applies in trying to study gravitational waves in general.